In today's lesson video, we're moving on to lesson 5.2, and you'll notice in your note packet that we're starting with a bell work day with day 1 and day 2 and so on and so forth, but I've put the bell work in front of each lesson. For my in-person students watching these videos, these are going to be your warm-ups you do at the start of your in-person class session after you've already watched the lesson video moving forward. All right, so if you are a virtual student or you're quarantined, you're watching at home and you're not going to be in an in-person class, you can do the bell work as just kind of a warm up or as a extra practice for the previous lesson. Okay, so this bell work is a reminder from our Pythagorean theorem lesson. Otherwise, we're going to go ahead and move on into lesson 5.2 over a couple main topics. And this video might take a little bit of time, a little bit more to cover here. But the first topic is the converse of the Pythagorean theorem, and then we're going to get into the concept of special right triangles. Special meaning unique. They have certain properties that are always true given certain sizes, and so there's shortcuts we can take. But first, let's talk about the converse of the Pythagorean theorem. You remember the Pythagorean theorem, a squared plus b squared equals c squared. But the converse of that, the word converse here just means the opposite wording. So in the Pythagorean theorem, you had to start with the fact that it was a right triangle. If it's a right triangle, then you know a squared plus b squared equals c squared. The converse of that says that you can look at any triangle, and if the three sides work out such that a squared plus b squared equals c squared, that can be used to determine that it is a right triangle. Okay, and so we're kind of going backwards in order. We're going to look at some given sides here and try and figure out, could these be sides of a right triangle? We're going to use something called the converse of the Pythagorean theorem, or the Pythagorean converse. Okay, so first we want to determine if the side measurements form a triangle at all. Now, you might not be real sure what I'm talking about there, so let me kind of illustrate that for you. If I have three numbers, and I'm saying those have to be sides of a triangle, those three numbers have to work out in such a way that the two smaller sides sum, okay, the two smaller sides, sum meaning add them, has to be greater than the longest side. Okay, the two shorter sides or smaller sides have to add up to more than the longest side. Okay, so if I'm using, I'll just use A, B, and C. A plus B must be greater than C to be a triangle. All right, where C is the biggest side, very similar to the hypotenuse in a right triangle. So if they do actually form sides of a triangle, then we can classify it using the Pythagorean converse. So we can determine, is it a right triangle or not? But beyond that, we can actually look at some special cases and figure out if it is an acute triangle or an obtuse triangle, like this. So we're going to start off with the Pythagorean converse. If a squared plus b squared equals c squared, then the triangle is classified as a right triangle. We know that one. And so if a squared plus b squared is something different than c squared, we can use that to classify it as either acute or obtuse. So let's start with when a squared plus b squared not equals, let me fix that, is less than c squared. That means that the length of c is actually longer than if it was just a right triangle. And if you could imagine that you have this right triangle and you stretch the hypotenuse longer, but you keep the other sides the same length, that's going to make your right angle bigger. So bigger than a right angle would be an obtuse angle. So if a squared plus b squared is less than c squared, because we made c bigger, it's an obtuse triangle. All right, and then similarly, if a squared plus b squared is greater than c squared, meaning we made c smaller, that makes that right angle smaller. Smaller than a right angle is an acute angle, so that makes it an acute triangle. Okay, and so it's kind of weird to visualize. I can help you out if you're having trouble with that, but these are the rules that we're going to be using in these next few examples. Okay, first you want to try this one. You want to see, is a plus b bigger than c? If it's not, then it's not even a triangle and I can't classify it as right, obtuse, or acute. Okay, so let's look at the numbers 3, 7, and 9. First, you want to figure out, do the two shorter numbers add up to more than the third number? C is always the biggest number. In this case, C is the 9. Okay, so I check 3 plus 7, which is 10. 10 is greater than 9. So this is a triangle. Okay, the two shorter sides add up to more than the third side. And so now we want to check it with Pythagorean converse. So we do a squared plus b squared, and then don't write equals, don't write anything yet in this space. We're going to compare it to c squared with an inequality or an equal sign based on the numbers. So a and b have to be these other two, the two shorter ones. So we'll do that 3 squared plus 7 squared on the left, and c squared is 9 squared on the right. 3 squared is 9, 7 squared is 49, 9 squared is 81. So when I add the 9 and the 49, that's only 58. 58 is less than 81, right? So a squared plus b squared is less than c squared, which means we're looking at this line, which means it's obtuse. Okay, a squared plus b squared is less than c squared, so this is an obtuse triangle. All right, so let's move on and check the next one. 4, 11, and 16. Again, check the two smaller ones to see if a plus b is greater than c. Okay, well, a and b are the 4 and the 11. 16 is the c. If I add 4 plus 11, that's only 15. 15 is not greater than 16. 15 is less than 16. This one's not a triangle. Can't be a triangle. I can't have two sticks that are 4 inches and 11 inches and put them together with a 16-inch stick and get a triangle. They won't meet. They won't form three actual angles. Okay. All right. Next one, 9 and 10. We want to check and see, do these numbers add up to more than the third number? 20 is the A, 21 is the B, 29 is the C. 20 plus 21 is 41, which is obviously greater than 29, so it is a triangle. Now we're going to check the Pythagorean converse, a squared plus b squared and c squared. Okay, a is 20, b is 21, c is 29. 20 squared is 400. I'll have to calculate these other ones. 21 squared is 441. And 29 squared is 841. So when I add these two on the left, 400 plus 441, it gives me exactly 841 on both sides. Since that's equal to itself, we know a squared plus b squared equals c squared. That equals makes it a right triangle. Our original Pythagorean theorem works. Okay. Number 10, as we look here, we've got 17, 17, and 22. Again, I want to add these up. 17 and 17 for the smaller two add up to 34, which is greater than 22. So we know this is a triangle. So I can move on to the Pythagorean converse. Okay, 17 squared is 289, so I have two of those. And 22 squared is 484. When I add 289 plus 289, I get 578. This time, 578 is greater than 484. That means a squared plus b squared is greater than c squared because it's greater than, this is an acute triangle, according to our rules here. When a squared plus b squared is greater than c squared, it's acute. All right, now as we move on, we're going to move on into another big idea from this unit. And this is fairly unrelated to the content we just covered in the first part of the video. So make sure you pay attention here. We want to take a look at what are called special right triangles. Now, a special right triangle just means it's a unique right triangle that has certain properties that allow us to always identify length measurements with even less information. Okay, the first one is called a 45, 45, 90 triangle. Now, let me explain where that comes from. When I take a square and I cut it in half with the diagonal like this, I'm splitting two right angles here to get 45 angles for each half, right? So when I cut a square in half, I get this special right triangle called a 45, 45, 90. That's because each of the acute angles is 45 degrees and then you have a right angle. Now, I want you to remember something. If both of these angles are 45 degrees, both of these angles are congruent, which makes this an isosceles triangle, okay? And since it's isosceles, that, remember, means these are congruent legs of that triangle. And so we're going to call each of those a leg. Now, I'm just going to use the letter x as a variable to represent the legs. If I were to work out the Pythagorean theorem with a little bit of algebra, the length of the hypotenuse would end up being the length of that leg x times the square root of 2 when I do exact or simplest radical form. So this is the pattern we get, and you need to kind of memorize this. In a 45, 45, 90 triangle, each of the legs is called x, meaning they're the same as each other, and then you take that length and multiply by root 2 to get the hypotenuse length. That's our shortcut. And so here's our relationships between the sides to find a missing side. If you're going from a leg, meaning you know the leg, and we're looking for the hypotenuse, you just multiply by a root 2, stick a root 2 on the end. If we're going backwards then to get rid of that or undo it, meaning I know the hypotenuse and I'm looking for the leg, we undo that multiply by root 2 by dividing by root 2. Okay, put a root 2 under it like a fraction. And so we're going to work on or get rid of it if it's there. So let's try some examples of these special right triangles. So in this one, we've got a 45 angle here. That means the other one is also 45. If they mark one of those angles with a 45 and it's a right triangle, you know it's a 45, 45, 90 triangle. It has to be. Okay, they give you these pieces. Well, this is a leg, this is a leg, this is the hypotenuse, right? Okay, the legs have to be the same as each other. So what does y equal? The same as the other leg, 25. I know y equals 25. No calculation needed. I just look at it. It's there. I know it. To find the hypotenuse, again, we know the leg. So we're just going to multiply that leg by root 2. So to find the hypotenuse, all I'm going to do is take that length for the leg, 25, and multiply it by root 2. That is my answer. I don't have to do any other calculations. The number underneath that radical is already a simplified number. It's as small as it can go. There's your answers. Okay, let's try that again for number 2. This time, they give me some more complex looking values here, but it's still a 45, 45, 90 triangle. These are congruent base angles. So the legs are congruent. So again, we know what y is. It's just that expression. I know y equals 5 root 2. We know the leg. So again, moving from knowing the leg to getting the hypotenuse, figuring out what x is, we're going to multiply by root 2. It's a little bit more involved this time because x is equal to the leg measurement, 5 root 2, times a root 2. Well, that means I have 2 root 2's I'm multiplying. It's like I'm doing root 2 squared. You should recognize when you multiply a root by itself, you get just the number underneath there. So that 5 stays there, but root 2 times root 2 is just 2, or square root of 4. Think of it that way if you want, but square root of 4 is 2. And then I can still simplify that to 10. The x value is 10. Okay, let's try one more. On this one, number 3, we've got another 45, 45, 90 triangle. It looks like I give you very little information. However, the legs are the same as each other. X equals y. They're going to be the same answer. I only have to do one thing. This time, I know the hypotenuse length. I know the hypotenuse is root 10, I'm sorry. Since I know the hypotenuse and I'm going to try and figure out the leg, we divide by root 2. So I take that root 10 and I divide by the square root of 2. Remember that when we divide radicals, we can just keep it under the same radical and divide the top and bottom number. 10 divided by 2. Well, 10 divided by 2 is 5. 5 can't be broken down anymore. So x and y are both the square root of 5. And those are your special right triangles for 45, 45, 90. Okay? we have one other special right triangle to look at, and that's a 30, 60, 90. All right, a 30, 60, 90. Again, special right triangle means there's just unique properties. It's a little more involved this time because I don't have two sides that are the same. So I don't have two angles that are the same either. Again, I'm going to show you where this comes from. All right, it actually comes from an equilateral triangle. If I split an equilateral triangle in half, remember equilateral, all the angles are 60 degrees. If I split that 60 in half at the top, I get 30 degrees. Okay, which is why I have this 30, 60, 90 triangle. Okay, so that's where we get that. Now, what that tells me is, remember it was an equilateral triangle. I'm going to start with the shortest leg given, and I'm just going to call that X. Because I originally took an equilateral triangle and split it in half, this would have been that full side of the equilateral triangle, which would have been like 2 of these X's, right? So that's 2x, it's twice as much. In a 30, 60, 90 triangle, let me erase a little bit of that. In a 30, 60, 90 triangle, the short leg, that's what we'll call that, is always half the hypotenuse, or rather the hypotenuse is twice the short leg, okay? Then for the rest of this, to find out what this other leg is, the long leg, we could use the Pythagorean theorem and do a little bit of work, but it ends up being x, the same length from down here, times the square root of 3 this time, okay? In 45, 45, 90 triangles, we used a root 2. In 30, 60, 90s, we use a root 3. 30, 60, 90 uses root 3. There's those 3's there, you can compare them up. 45, 45, 90 uses root 2. There's 2 45-degree angles, so we use root 2. That's a way you can remember which one gets which root. So here are the relationships. Again, if we know the short leg and we're looking for the hypotenuse, you multiply by 2. So I'm going to jump down here. If we know the hypotenuse, but we're going to the short leg, trying to figure that out, we divide by 2. Okay, those are opposites of each other. Okay, going back up, if we know the short leg and we are looking for the long leg, you just multiply by root 3. So going backwards in that, if I know the long leg and I'm looking for the short leg, you divide by that root 3. Okay. Now backwards is kind of the other idea we have here is when I know the long leg, what I like to do is actually go back and find just the short leg by dividing by the root 3. Then I can do whatever I need to from there. If I need to go from that short leg now to the hypotenuse, I just double it, multiply by 2. Okay, so there's some other rules there you can look at. So here's what we're going to do. We're going to find each of these measurements. Again, we're not using Pythagorean theorem. We're using our special right triangle rules because on each one of these, I'm only giving you one side length. Okay, for number 4, we have 2 things we're looking for, x and y. X is the long leg. How do I know it's the long leg? It's across from the 60-degree angle. It's the bigger out of the 2 legs. It looks bigger. And then y is the hypotenuse because it is across from the right angle. Again, that's the easy one to figure out. Hypotenuse is usually the easy one to figure out if you know the short leg. We take the short leg and we double it to find the hypotenuse. So y is 2 times 5, or 10. But to find x, that's the long leg. Again, we know the short leg. We're trying to find the long leg, so we multiply by root 3. So that x length is my short leg 5 times root 3, or 5 root 3. And that's how I write my answers. Okay, let's move on to another example. Here we know this length is 9 root 3. This is my x. This y is actually my hypotenuse. That means 9 root 3 is either the short leg or the long leg. Well, if you look at it, it looks longer than this side for x. So that's one way we can tell, but it's also right next to the smaller angle. So this other angle would be my 60. So again, it's across from the 60-degree angle. It's the long leg. So to go from long leg back to short leg, we get rid of that root 3. We divide by root 3. So we take that 9 root 3 and we divide by root 3. Well, since it's already got a root 3 there, you're just canceling it. You're getting rid of it. So x is just 9, okay? Then the hypotenuse is twice the short leg, twice x. So y is 2 times that 9 we just got, or 18. All right, one more example. As you're looking here, number 6, this time it's one of the more tricky ones because I'm giving you the hypotenuse. All right, I'm giving you the hypotenuse. What I like to do first is work from hypotenuse back to short leg first, because all you have to do, if you know the hypotenuse and you're going back to the short leg, you're just going to divide by 2, okay? So to go from hypotenuse back to y, we take that length and we divide by 2. So I take that root 5 and I just divide by 2. There's nothing you can do with that. That's already in simplified form. So to go from that short leg now to, y equals root 5 over 2. To go from that short leg to this long leg x, remember, from short leg to long leg, you multiply by root 3. So I'm going to take that length here and multiply by root 3. Well, what I like to do actually is put that root 3 up there in the denominator, because to multiply a fraction by a whole number, it's like you're doing that over 1. So the bottom of the fraction doesn't change. It's still over 2. That root 5 and root 3 on top can combine to be root 15. And 15 doesn't divide by any of our perfect squares. Okay, they're still up here from when I had them last time. So that is my final answer. That's as simple as we can write those. So a lot of what we're doing with these problems is just copying down numbers or writing numbers in a certain form and putting like values together. Put radicals together, put numbers that are not radicals together. Okay, we've got just a little bit more here. And these are our composite triangles. The word composite just means we're composing them, putting them together, all right? So we're going to combine all the rules that we've just used to find these missing pieces. So what you want to do is start with the triangle out of all the triangles given in the picture that you know the most about, okay? And then find those values and use those to move on towards the triangle you know the least about. So on this one, the number 7 picture, we know this is a 45, 45, 90 triangle here. And we know one of the sides, one of the legs, in fact. We know the most about this one. We don't have any other side measurements to go off of in the other triangle. But since you know that it's a 45, 45, 90 triangle, remember the legs are the same as each other. So this is my other leg, 32. And the hypotenuse is just that length 32 times root 2. You just add a root 2, or not add, sorry, multiply by root 2 on the end. So the length of x is 32 root 2, okay? Now that 32 is also the hypotenuse of this 30, 60, 90 triangle. And to go from hypotenuse back down to short leg, you just divide by 2. Okay, short leg times 2 equals hypotenuse. So to go backwards, divide by 2. 32 divided by 2 is 16. So z is 16. Y is the long leg. To go from short leg, 16, to long leg, you just take that number and multiply by root 3. So y is just 16 root 3. Okay? All right, one final example. Very similar to what we just started with, but this time I know the most information about my 30, 60, 90 triangle. I know the hypotenuse length. Okay, I know that length there. That's going to help me find a few things. First of all, to go over here to this x value, that's the short leg on the 30, 60, 90. Remember, from hypotenuse back to short leg, we divide by 2. Okay, I don't want to multiply by 2. You can look at this and tell the hypotenuse has to be longer than the short leg. So I don't want to get bigger, I want to get smaller. Divide by 2. So 12 divided by 2 is 6. So x is 6. And then I'm going to use that to finish out, even though it's not one of the variables they ask for, finish out with the long leg, which means I take that 6 and I multiply by root 3. That's the long leg of my 30, 60, 90, but it is also just the leg of the 45, 45, 90. So that means the other leg, y, equals that same thing, 6 root 3. So y is 6 root 3. Okay? All right, and then to find z, our final variable here, all we have to do is take our leg length, 6 root 3, and multiply it by root 2. In a 45, 45, 90, you take your leg times root 2 to get your hypotenuse, and z is the hypotenuse. So that means I can combine these two together, keeping this 6 in front. Root 3 times root 2 is root 6. Nothing there simplifies. 3 and 2 are the only factors of 6. Neither of those is a perfect square. So the length of z is 6 root 6. Okay, now that finishes our lesson video for 5.2. You'll see it says quiz next class. Okay, so again, not the class where you actually do this assignment, but the following one. After you've done a complete assignment over 5.2, then you'll have a quiz. Okay, this bell work will be a review for that quiz. So if you're an in-person student, we'll do that in class. If you're a virtual student or quarantined, you can use these bell work problems as your practice before doing the quiz. Feel free to reach out to me with a message and I will tell you if you're doing them right or wrong.